Excited today. This is our annual Peterson Lecture, and before I introduce the speaker, I will first introduce Mr. and Mrs. Peterson, Jane Peterson and Mary Peterson, who are here. Because of their support and generosity, this lecture is possible. I'm very grateful. To the crowd?
Yes, sir, thank you. Well, this vast crowd, this is really good. That's also exciting. I'd like to see the young people, the students, and this is what this lecture was designed for, to show people how exciting physics really is. And there's something else that I'd like to say, that there were two men, Edwin Hubble, decades and decades ago, that changed the face of cosmology. He's no longer with us, but the other man is, and that is our speaker, Dr. Allen. When I shook hands with him, I said, I feel like I'm shaking hands with Babe Ruth. Sir? Yes, sir.
Well, I had a bag full of introduction, but after that, what do I need to say? We have Professor Alan Good for this lecture, speaker of the lecture. And as you know, if you have read his book, it's Mr. Grand Unified Theory. Good, G-U, Theta. That's how he describes himself. And so without further introduction, we are all waiting for him telling us about going from universe to multiverse. Oh, I'm so excited.
Okay, well, I'm glad to see you all, except I think my application is too loud, probably. Oh, it's not you. Oh, good. Okay, does it sound good? Okay.
If you can't hear in the back or anything, yell and scream, and we'll do something about that. I must say this is a beautiful auditorium, but I actually hate the idea of having the two screens here. I'm used to walking around and pointing with my laser pointer. And to make this work, I think I have to sit with my computer and point from the screen. So I don't know if I can actually give a lecture without walking around. I'll try. It must be possible, I guess, but I'm not used to it. But I'll do my best. What I want to be talking about today is the idea that inflationary cosmology really might lead to a multiverse in which we would be living. I'll begin by reviewing what inflation is, and for some of you who were at my lecture yesterday, there will be some repetition there at the beginning. But once I get going talking about the multiverse, things will be different from what I said yesterday. Hopefully not contradictory, but other topics. The idea of a multiverse has become something which is much more widely talked about now than it was, say, a decade ago. The idea certainly is by no means an established fact, but it is something which cosmologists take seriously. Nowadays, in almost any cosmology conference that I might go to, there's a session about the possibility of a multiverse. At first, the idea of talking about a multiverse might sound more like science fiction than science, but I would argue that that's not really true. Science never talks about anything that happens only once. If one just thinks about the vocabulary of the English language, as far as I can identify, there really are only two nouns in the entire language that people sometimes think there's only one of, and that's God and universe. And if we want to have a scientific approach to the universe, I think we are much better at thinking of universe in the same kind of way that we think of galaxy and supercluster and star, rather than equating it with God. So I think it really is a very natural scientific approach to think of the universe as being one of a possible set universes. And I will argue that that seems to be what inflation is pointing towards. So, I want to begin by just reviewing what inflation is, and in fact, I'll even start with the same slide I started with yesterday, giving a short review of what the standard Big Bang is before inflation, to be able to set the stage for what inflation does. So the conventional Big Bang theory, as it was known before inflation, is basically the theory that the universe, as we know it, began some 13 to 14 billion years ago, and now we think we even know very accurately how long ago that was, 13.82 plus or minus 0.5 billion years ago, according to the latest analysis based on the satellite data. The initial state for this universe was a hot, dense, uniform soup of particles. These particles had to fill the entire space to begin with, and we also assumed that they were rapidly expanding from the very beginning. The theory describes how the early universe expanded and cooled. It describes how the light chemical elements formed, and to make sense out of that, I should point out that this model starts describing the universe at a time when the temperature was so hot that even the nuclei of atoms would not have been stable. So we start out basically with a soup of quarks, which later form protons and neutrons, which later form nuclei. And since the model really gives us the capability of calculating how fast the expansion would be, how fast it would be slowing down, what the temperature would be at any given time, all those things can be calculated in the context of this Big Bang model. And that gives us a framework for being able to calculate the nuclear reactions that would have taken place. And these really are the same energies at which one can explore nuclear reactions in reactors and accelerators. So that means that we're able to calculate what the expected abundance would be of the different light chemical elements. It's only the lightest chemical elements that were produced primarily in the Big Bang. Most of the elements we see around us were actually produced much later in the interior of stars. But the lightest chemical elements were produced primarily in the Big Bang. We can predict what their abundances should be, and those calculations work. We really do get successful predictions for the abundances of the lightest chemical elements. And that is one of the primary pieces of evidence that tell us that this Big Bang picture seems to be correct. The Big Bang theory also tells us how matter congealed to form stars, galaxies, clusters, and so on. That's still a work in progress. We don't have a complete theory of structure of the universe, but it's certainly a subject on which a lot of progress has been made, and things do seem to fit together. There are no real contradictions of any kind that have been discovered. So that's what the standard Big Bang theory tells us. I want to move on next, though, to what it does not describe, which is the important background to where inflation is going to fit in. And the rough answer to the question of what the Big Bang theory does not describe is simply that it does not describe the Big Bang. In spite of the name that it has acquired, the one thing it really says nothing about at all is the Big Bang itself. The scientific version of the theory of the Big Bang is truly a theory of the aftermath of a bang. It starts with the matter already expanding, and with every particle that exists in the universe already existing. It tells us nothing about what caused the expansion or where all of this matter came from. I like to summarize this by saying that the Big Bang theory tells us nothing about what banged, why it banged, or what happened before it banged. So those are the kinds of questions that it turns out inflation can provide a possible answer to. And that's what we'll move on to talk about now. So cosmic inflation is a twist on the Big Bang theory. It by no means replaces the Big Bang theory, rather it just modifies the Big Bang theory. And what it really does is it provides something which I think can only be described by a Hollywood word. It provides a prequel to the Big Bang. It's the story of what happened before the story that was already known about the early universe. So, in particular, inflation can explain the bang of the Big Bang, that is what caused the propulsion that drove the universe into the period of expansion. And it describes it, I like to use the language, some of you heard me use this yesterday, in terms of a miracle of physics. Now, physicists, I think the technical rules are that we're allowed to believe in miracles if we want to, but we're not supposed to use it to explain physical phenomena. But what I'm talking about here as a miracle of physics is not quite a miracle in the usual sense. But from my point of view, there are a few features of the laws of physics as we know them, which are A, so different from what I learned when I was a student, and B, so miraculous in terms of the dramatic consequences that they can lead to, that I think it's fair to call those laws of physics miracles, even though they are completely within the laws of physics as we know them. So the first miracle here, which is what provides the bang of the Big Bang in the context of inflationary models, is the fact that gravitational fields can act repulsively. According to Newton, gravity is always attractive. We all learned about that. But it turns out that as soon as one introduces general relativity, rather than Newtonian physics as the description of gravity, then there are both attractive and potentially repulsive contributions that can exist. And this repulsive form of gravity was actually introduced by Einstein early on in the form of what he called the cosmological constant. His cosmological constant was an extra term that he added to the field equations, which he added for the purpose of creating a repulsive force. Einstein, if you know the history, was convinced that the universe was static. When he built his theory of general relativity, he noticed something which, in fact, Newton could have noticed but didn't, which is that if you try to suspend masses uniformly in space and expect them to stay there, they won't, because everything attracts everything else, and the whole thing collapses. And this is, from modern context, viewed as a feature of Newtonian mechanics as well as a feature of general relativity. It was really Einstein who pointed that out in both contexts. So, to keep his static model of the universe, Einstein introduced this extra term, which produced a repulsive force, all in the context completely consistent with the theory of general relativity. From a modern point of view, this term that Einstein introduced has a different interpretation than Einstein gave it. We interpret it as simply being the energy density of the vacuum. Now, sociologically, I think it's sort of clear why Einstein did not look at it that way, because Einstein was living in an era before quantum field theory, for example, and actually before quantum mechanics being generally accepted, and before, in particular, Einstein accepted quantum mechanics. In the classical world, the vacuum is just empty, and watching emptiness have any energy density. So when Einstein wanted to have this extra term, he just considered it a new term in the equation that describes how gravitational fields are created. However, in the modern context, where we view empty space as being described by quantum field theory, in quantum field theory, empty space is really not empty at all, because the uncertainty principle, which applies to the quantum fields in the vacuum, do not allow them to be quiescent. So in the vacuum, as seen from quantum field theory, there's a constant nucleation of particle-antiparticle pairs which form and then annihilate. We also think there's this Higgs field that you've heard about, which has a non-zero value even in the vacuum. So the vacuum is not at all simple, not at all empty. What defines the vacuum in the context of the quantum field theory is that it's simply defined to be the state of lowest possible energy density. But it's by no means empty, and it's not at all obvious why its energy density should be zero. In fact, we really don't understand at all why it's even anywhere near zero. So from a modern point of view, it's very natural to believe that the vacuum can have a non-zero energy density. And if you allow for that and put it into the equations, it has exactly the same form as the cosmological constant that Einstein put in. So from our point of view, that is the cosmological constant. And you may have heard that we now believe that the energy density of our vacuum is positive, because we've seen that the universe is accelerating. And that means that we have a positive vacuum energy or a positive cosmological constant. What inflation assumes is that during the early universe, there was a much larger, effectively vacuum energy density, which drove an incredibly rapid gravitational repulsion, resulting in exponential expansion. So with the combination of general relativity and modern particle theories, there really is a prediction that at very high energies, there should be these peculiar states of matter which act like vacuum energy and produce gravitational repulsion. What's really required in the context of general relativity to create this gravitational repulsion is a negative pressure. And vacuum energy is known to have such a negative pressure. If you want the question, you can try to ask me why, but for now I'll skip over that. So inflation proposes that a patch of this repulsive gravity material existed in the early universe. For inflation to work, we should confess here we don't really know the energy scale at which inflation happened. The most plausible place where inflation can happen is presumably at the scale of what particle physicists call grand unified theories, which is an energy scale of about 10 to the 16 GeV, billion electron volts. And if that's the scale, the patch needs to be only as large as 10 to the minus 28 centimeters, which is unbelievably small. And